Let's start lecture. Capacitors and dielectrics. Capacitor is a device that stores electric potential energy and electric charge. To make a capacitor, just insulate two conductors from each other. Capacitors has widely used in various electronic devices such as flash memory, radio receivers, and television receivers, and so on. In this lecture, we will focus on the fundamental properties of capacitors, such as capacitance calculation, physical meaning of capacitor, electric density calculation, and capacitor with dielectrics. Firstly, let us review electric potential of point charge. When we move this test charge from infinity far to distance r, the work required to move the test charge Q0 can be calculated. It is equal to electric potential times Q0, test charge Q0. The potential between this Q0 and big charge Q is equal to 1 over 4 pi epsilon 0 times Q divided by small r. Here, we use infinity as the reference point, which means no physical interaction between big Q and the test charge when test charge is at infinity. Now, let us assume Q is placed on the metal sphere. The electrical potential between this Q and this Q0 is equal to 1 over 4 pi epsilon 0 times Q divided by R. And then, let us place more electric charge onto this sphere, metal sphere. And then, we can find this potential will increase. Generally speaking, for any isolated conductor, increasing its charge always leads to increase in electric potential. However, the ratio between charge amount and electric potential keeps constant. For this isolated conductor, this ratio is equal to Q divided by this delta V, potential difference. It's equal to this 4 pi epsilon 0 R. Because R is fixed, we just add more electric charge. So R is fixed, this is constant. This constant is called capacitance. Many experiments have shown the ratio between charge amount and electric potential is constant. We use this C, to express capacitance. Its international unit is Faraday, which is a derived unit equal to 1 coulomb divided by 1 voltage. In circuit diagram, we use these two symbols to express capacitors. This line means metal wire, and these parallel lines means two conductors are separated. Capacitance build a relationship between potential difference and stored charge. It means capacitor can store this charge and also can store electrical potential energy. These are capacitors. In Germany, it is called condenser. It's similar to Japanese condenser. Capacitor has various types. The simplest form is parallel plate capacitor. These two metal plates are separated by a distance d. When the plates are charged, electric field is almost completely localized in the region just between plates. The field between such plates is essentially uniform. Because generally speaking, in capacitor, this d is very small compared with this size area. Now, let us calculate capacitance of parallel plate capacitor. In order to calculate capacitance, we need to calculate electrical potential firstly. In last lecture, we studied electrical potential can be calculated from electric field. We want to calculate capacitance. Firstly, we should know this electrical potential difference. And then, how to calculate this electrical potential difference? We should know electric field, firstly. And then we can calculate. This is the calculation process. Firstly, let us draw electric field line for this parallel plate. Electric field line starts from positive charge and into negative charge. At the edge, their distribution, electric field distribution, is different from that at the center. This is because of bridging effect. However, when this separation distance is very small compared with the size area, we can neglect bridging effect. Moreover, because of attractive force between this positive charge and negative charge. So most charge will be distributed on this side and less charge on this side. If this plate is very uniform, all the charges will be distributed just on this side. So the charges on the plates are uniformly distributed over the opposing surfaces. This is idealized model. Generally speaking, the plate is not uniform. All the charge cannot just distributed on one surface. Then we can use Gauss law to calculate electric field. Because the electric field is uniform distributed between these two plates, we can draw imaginary column as a Gaussian surface. This is a closed surface, column structure. Firstly, let's say this S2. Its bottom surface just inside the plate, and no charge enclosed in this S2. So electric flux is 0, and then the electric field must be 0 outside this parallel plate. In physics, we can think electric field generated this E1. Electric field E1 generated by positive charge can cancel out with electric field generated by negative charge. Just cancel out, so electric field outside is 0. On the other hand, for this S1, because all the charge distributed just on this surface, electric flux through this column should be equal to EA. A is this surface area. Electric field times A, and equal to total charge, surface charge density times area, and then divided by epsilon 0. Lastly, electric field inside this parallel plate capacitor is equal to sigma divided by epsilon 0. It's constant. This calculation is based on the application of Gauss law we studied in lecture 2. Please review. Next, let us calculate electrical potential. Electrical potential between two plates can be expressed by delta V is equal to electrical potential A minus electrical potential B. We can select infinity far as a reference point. For electrical potential A, it can be expressed as this one. Please just imagine. There is a test charge move from infinity far, go to this plate A. Firstly, we can move this test charge outside plate B, and then move inside this parallel plate, and then to approach plate A. So this is the two parts. One is from infinity far go to B, and then from B to plate A. On the other hand, electric potential of plate B can be expressed by this. This is just move test charge from infinity far to plate B. So, the difference between electric potential is equal to this. This is because electric field outside this part is 0. Outside electric field is 0 outside the parallel plate. Also, this is 0. So only this term remains. We can write like this. Because this electric field is constant inside this parallel plate, so we can move this electric field outside the integral and obtain formula like this one. Here, integral from a to b at dl, this is line integral. It's equal to distance between two plates. So the result becomes electric field inside times distance d. Just now, we studied electric field inside the parallel plate is equal to sigma divided by epsilon 0. So we can use sigma divided by epsilon 0 times d. Here, sigma is surface charge in density. It is equal to total charge Q divided by surface area A. Then we can calculate capacitance C. It's equal to Q divided by potential difference delta V. So Q divided by this is equal to epsilon 0 times A divided by distance D. From this formula, we can find the capacitance depends only on the area A and separation distance D. This means capacitance for parallel plate capacitor depends only on the geometric factors. Here, I want to make a wave episode. When we calculate electrical potential, here we use infinity far as a reference point. In fact, we don't need to do this. We can select plate B as a reference point, just as like this formula. We can select this plate B as a reference point to calculate. The difference between A and B has a physical meaning. Another typical capacitor is a spherical capacitor. A spherical capacitor consists of two concentric spherical shells of radius A and B. The inner shell has a charge plus Q uniformly distributed over its surface, and the outer shell has a charge minus Q. In this case, how to calculate its capacitance? Similarly, we firstly calculate electric field and then calculate potential difference. Lastly, we can obtain the capacitance by this formula. Because there exists spherical symmetry, so we can use Gauss law to calculate electric field firstly. We can draw Gaussian surface inside the shell, just like this one. Based on the Gauss law, the total electric flux out of this Gaussian surface is equal to E times 4 pi r squared. And then it equal to total charge inside Q divided by epsilon 0. So electric field inside this shell is equal to Q divided by 4 pi r squared times this epsilon 0. Just like this. On the other hand, for the electric field outside the shell, larger than B, because the total charge inside this Gaussian surface is plus Q plus minus Q, so net charge is 0. So electric field outside this condenser is 0. Sorry, capacitor. This is a calculation for electric field. And then we can calculate potential difference between two shells. This time, we can select plate shell B as a reference point, and then to move test charge from B to this radius A. Test charge from B to A, and then this is the electric field inside this part from between outer shell and inner shell. And then substitute electric field into this integral, and then we can obtain the last result as Q divided by 4 pi epsilon 0 times this B minus A and divided by AB. Thirdly, we can obtain the capacitance use this formula. Its capacitance is equal to 4 pi epsilon 0 times AB divided by B minus A. Also, its capacitance depends only on the radius A and B. Now, let's start third case. Cylindrical capacitor is also very typical. A solid cylindrical conductor of radius A, this part, surrounded by a coaxial cylindrical shell of inner radius B. The inner cylinder has a charge plus Q, and the outer shell has a charge minus Q. Here, please note this length L is much larger than B minus A. What is capacitance? The calculation process is the same. Firstly, based on Gauss law, we can calculate electric field between inner cylinder and outer shell. When L is much larger than B minus A, it means freezing effect can be neglected. So, we can use this column as a Gaussian surface. We have studied this example in the second lecture. Electric field only point outward, only point to this Gaussian column surface. Electric field cannot point along this charged line. And the total electric flux should be equal to 2 pi r, this is r is the radius, 2 pi r times L, this is circle length, and then times the electric field E. Based on Gauss' law, total electric flux is equal to total charge divided by epsilon 0. Here, total charge can be expressed by this length times charge density lambda. This term is equal to this term, so we can obtain the result: electric field inside the cylindrical capacitor is equal to 1 over 2 pi epsilon 0 times lambda divided by R. Then we can select out shell as a reference point. Here we can select this point as a reference point and then move test charge Q0 from this point to A. And then substitute electric field inside and then obtain the final result, have this form. Lastly, we can calculate capacitance as Q divided by potential difference. The capacitance is equal to 2 pi epsilon 0 times length L divided by log in B over A. From this expression, we also find capacitance depends only on the length L and radius B at A. Only depends on the geometrical factors. So far, we talked about 3 typical capacitors. Let me make a brief summary. For parallel plate capacitor, its capacitance is equal to epsilon 0 times surface area A divided by separation distance D. For spherical capacitor, it's equal to 4 pi epsilon 0 and then times radius A times radius B divided by difference between these two radius. For cylindrical capacitor, its capacitance is equal to 2 pi epsilon 0 this times this length divided by log in B over A. All of these capacitance only depends on the geometric factors. Based on this information, this makes us enable to design capacitor by ourselves. Just design geometry of capacitors. Okay, let's take a rest and continue.